Okay. So the simplifying radical expressions, the most basic is, right, if you're taking the square root of x squared, how would that simplify? Right? It's like the square root and x squared are inverse operations of each other. So they cancel each other out, and all you get is the x. Right? Just like the third root of x to the third, they cancel each other out, and all you get is the x. Right? I mean, another way you can think about this, because we're not always going to have exactly the same power of x as the index of the radical. So the way you figure out how many x's you take out is you do whatever the power is inside, you divide it by the index. So 3 divided by 3 means x, 1x comes outside. So in this one here, the fourth root of x to the fourth, right? How many x's come out? 4 divided by 4, it's 1. Does that work with x, the square root of x squared? What is the index of the square root? What is the number? There's like an implied 2, so it works. The same rule works, just that we don't usually write the 2, the index of 2 for the square root. It's assumed to be there. All right, now, when you have the square root of x to the third, all right, now, you know, you're going to be able to take out some x's, but not all of them. So the way I think of it is like this. I'm going to say, does 3 divide evenly by 2? No. So try to split it up into 2 x's. What's the greatest number less than 3 that is divisible by 2? 2. So split it up into x squared times x. Now, by our properties of exponents, is x to the third equal to x squared times x? Sure. So now we'll take the square root of x squared times the square root of x. And the square root of x squared we already did. That's x times the square root of x. Right, the next one, the third root of x to the fifth. Does 5 divide evenly by 3? No. What's the greatest number less than 5, which is divisible by 3? 3. So what are the two x factors here? X to the third times x squared, right? They got to add up to 5 by properties of exponents. So now we're going to take the third root of this and the third root of that. And the third root of x to the third, we already did, right? That's x. And then we still have the third root of x squared. And you can't simplify that because the power that's inside is already smaller than the index, right? There's no way for me to break it into parts or anything. How about the fourth root of x to the seventh? How can I split up the x's so I get maximum simplification? Josh? So it'll be x to the fourth and right. They got to add up to 7, right? Properties of exponents. So this is the fourth root of x to the fourth, the fourth root of x to the third. And the fourth root of x to the fourth is x. Right? That's just the starting point. Okay, now it won't always be, you know, as simple as the last slide. Sometimes there's going to be some numbers involved. Sometimes there'll be more than one variable. the square root of 49x to the fifth. You could consider that, break it into 2. Break it into the square root of 49 times the square root of x to the fifth. So when you're simplifying the numbers, you got to think to yourself, is 49 a perfect square? Yes. So we don't have to do anything to break that into factors for simplification. It's going to simplify. What about the x to the fifth? Is 5 divisible by 2? Because it's a square root, that's the index? No, it's not. What's the greatest number less than 5 that is divisible by 2? 4. So we want to split this up into x to the fourth times x, right? But you want maximum simplification, right? In your mind, you may say, well, I'm going to do x squared, right? But if you have x squared times x to the third, you still got some simplifying to do. You want maximum simplification. So now we can do the square root. The square root of 49 is 7. The square root of x to the fourth is x squared, right? 4 divided by that invisible index of 2 gives you x squared. And then we've got the square root of x, which cannot be simplified. Right, the next one, right, the square root, the third root, sorry, of 125x to the ninth y to the fourth. Let's break that down. We'll make that the third root of 125 times the third root of x to the ninth times the third root of y to the fourth. All right, so now, again, you got to ask yourself, is 125 a perfect cube? Yes, right? What number cubed equals 125? 5. 5. Remember, if you don't remember your perfect cubes, you can do this. In fact, I usually say do it for the squares and the cubes. In your calculator, on the y equals, the first line put x squared, the next line put x to the third, and then look in the table of values, second table, and the first column there's all your perfect squares. The second column, there's all your perfect cubes. So look in the list. Is 125 there? Yes. What number cubed equals 125? 5, right over there. Okay? Okay, now this, John. Okay. Well, what about this, the third root of x to the ninth? Is 9 divisible by 3? Yeah. So yes, so we don't have to break that apart. What about the third root of y to the fourth? Okay, what are the two? Y to the third times y, right? And now we'll get the third root of this, the third root of that. So this whole thing will simplify as the third root of 125, 5. The third root of x to the ninth is x cubed, right? We got to go 9 divided by 3, x to the third. The third root of y to the third, y, and then the third root of y. The third root of 54x to the fifth, okay, is 54 a perfect cube? Look in the table of the perfect cubes. Do you see 54? Okay. Is it divisible by any of the perfect cubes? Curtis, calm down. Okay? It's the last time I'm warning you. Understand? 27, right? So you should go, if you're not, totally comfortable with these numbers, start with the first number, which is less than 54, and divide, and see whether it divides evenly. 54 divided by 27 is 2. So we'll do it like that. And honestly, whether you split this up into a bunch of different radicals every which way, it's whatever works for you. I'm just going to go like this. This will be 27 times 2. And then the x to the fifth, does 5 divide evenly by 3? No. So how should I split the x's up so I can get maximum simplification? 3 and 2, right? So it'll be x to the third times x squared. And now we take the third root of every one of them. Okay, the third root of 27 is 3. The third root of 2 can't be simplified. The third root of x to the third, x. The third root of x squared can't be simplified. Okay, and then for a last step, put all the things together that are outside, right? That'll be 3x. Put all the things together that are inside the radicals, the third root of 2x squared. Good, good. Logan? Okay. So try that one. The what? Second graph. Look above the graph button. What does it say? Okay. Was 128 a perfect cube? Did it have any factors that are perfect cubes? 64. So that's on the 128 part, 64 times 2. Did you get an answer? What'd you say? um, that x to the fourth, 4 is bigger than 3, so you could split that up again. There was more simplification to do. The way you broke up x, you could have had more simplification. Again, you wouldn't have it, if you've got an exponent inside that is bigger than the index, that means you can simplify it some more. That you probably shouldn't have split it up between x to the third and x to the fourth. What should you have done? Remember, when you say to yourself, is 7 divisible by 3? No. What's the greatest number less than 7, which is divisible by 3? That's 6, not 3. Everybody that I see is broken up x to the third times x to the fourth. Not correct. Right? If you have inside the radical, if you've got the third root of x to the fourth, okay, well, then there's more simplifying to do because the power inside is bigger than the index. Right, so it should have been split up into these parts. And then when you simplify, we'll get 4 times the third root of 2. We get x. How many x's come out of that? 2, right? 6 divided by 3. 6 divided by 3 is x squared. And then the third root of x. And then get everything together that's outside. That's 4x squared. And everything together that's inside, that's the third root of 2x.
Where did 4?
The third root of 64. Okay, then they introduced this property. They call it a product property. I mean, the truth is, we've kind of been doing this already without calling it a property. This is the reverse of it. Not really. I mean, in a way, when we went from the square root of 2, or the third root of 2 times the third root of x, and we put it together as the third root of 2x, that's what that property is. But now we're giving it a name, the product property. Right? The product property says if you have the product of radicals, you could make that one radical of the product. So in the first line here, the square root of 2 times the square root of 8 can be turned into this one square root, right, of 2 times 8. Right? Now, the 2 times 8 is 16, so the square root of 16 simplifies. Right? The square root of 2 didn't simplify, and the square root of 8 didn't simplify, but the square root of 16 does. So sometimes by combining, you're going to get some simplification that you wouldn't have gotten before. How about the second line? How can I rewrite the third root of 2 times the third root of 32? Yeah, just put it in one radical. You know, you're probably not going to write it like that. You're probably just going to write 64, right, when you put it together. But just to show it, because we just introduced the property, we'll write 2 times 32, which is the third root of 64, which is 4, right? It seems to be our favorite cubed root today. Yeah. I don't know. You say the only. I mean, that there's a heck of a lot of numbers that are out there, you know. So try to think of how could you come up with a formula? Would you generate something like that? In class in college, I tell you, in math in college, the first classes you get to are like continuations of this kind of stuff, calculus. Then you get into, okay, just say calculus. And that's where like all the engineers, they stop, right? And then above that, if you're a math major like me, right, then you go into all kinds of like different kinds of math. And one of them is number theory. And number theory would be the kind of class that they would ask that kind of question. I don't think I have any books left on number theory. You good? We're done. Okay, so you try that one. Try to do a product property on that. How'd you put that together? What did it equal when you multiplied them together? The square root of 24 x to the 6th. Okay, so now you got to simplify the square root of 24. Right? Again, look at the calculator. Is 24 a perfect square? No. Does it have any factors that are perfect squares? Which one? 12 and 2. Neither one of those is a square, right? 4 times 6, right? Just start going down the list, from the top to the bottom, right? And that would be, it's kind of like if you, let's say you had to find the factor, what's the greatest factor of 72, which is a perfect square? Well, you've got 4 and 6 and 36, right? You want the greatest one. That's why you start at the biggest numbers, and you only have this one, 4. So let's see, if I split this up into a 4 times 6, then I'll be able to simplify part of it. How about the x to the 6th? Do I need to break that up? What's the square root of x to the 6th? X to the 3rd, right? So then we've got the square root of x to the 6th. This is 2 times the square root of 6 times x to the 3rd, which is 2x to the 3rd times the square root of 6. Good. Now, I'm going to show this one because you got a homework problem that's like it, and it usually causes questions. Because it's not just the radicals, but they actually, each radical's got a coefficient in front of it. And what do you think we would do with those? Just multiply them, right? I mean, just combine them before you start. That's 3 times 2. There's your 6, right? And then you can put the rest together. That's the third root of 5 times 50, which is 250. Y to the third times y to the fourth, y to the seventh. So it's just those numbers in front just stay in front. Right? Don't let that confuse you. Just deal with the radicals. At the end, you'll have a 6 on them. Right? Okay, now is 250 a perfect cube? Look in the list, right? You go from 216 to 343, 250, not in the list. So start going down the list. Is 250 divided by 216? No. 250 divided by 125? Yeah, times 2. So that is the factor. And these numbers that they use in this chapter almost always are going to simplify. I mean, they're not giving you numbers that won't simplify. So you just have to look for what it is. So this is 125 times 2. How about that y to the 7th? What do I need to do to that? Trevor? Okay, how would I simplify it? Y to the y to the 6th, right? Since 7 doesn't divide by 3, the greatest number less than 7 that does is 6. So make it a y to the 6th times y. And now we still have our 6 in front, and we've got the third root of everything. Six times the third root of 125, 5. Right, times the third root of 2, times the third root of y to the 6th, y squared, times the third root of y. Can't simplify. Okay, now put everything together, which is outside the radicals. 6 times 5, 30, y squared, and times the third root of 2y. So when you see that problem in the homework, you'll recognize that this is right next to it. Right? I did the even number one. Yours is the odd number one just before it. That's what you do with those numbers.
What did you do there to get that?
To get what?
To get the final answer.
From here to here? Okay, there's the 6. The third root of 125. Josh, you paying attention? Right, the third root of 125 is what? 5. There's the 5. Okay. The third root of 2 is that. The third root of y to the 6th is y squared. And the third root of y is there. So, I mean, I just wrote down these things, simplified what I could, this one and this one. Okay. Good. Okay. Now we also have a quotient property. Right? The quotient property says if you have the quotient, meaning the dividing of radicals, you can put those together into one radical. Or if you have one radical of a quotient, you can split it into 2. I mean, you can go either which way, right? It goes both directions. So like the square root of 32 over the square root of 2, you could write that as the square root of, and then put the 32 over 2 inside that one radical. And 32 over 2 is 16, and that again simplifies as 4. how about the third root of x to the fourth over the third root of x? How could I put those together? Right, make this the cubed root of x to the fourth over x. You know, once it's inside the same radical, then there's going to be some canceling you can do. And there's two distinct problems that we're doing here, right? The first set of problems, when we divide, the denominator will always divide into the numerator. Right? You'll never have a radical left in the denominator because it'll divide into the numerator or simplify in some way. Right? This one turns into the third root of x to the third, right? X to the fourth over x to the first. You could just think, you know, x cancels with one of the x's, or you could do the properties of exponents. 4 minus 1 is 3. And then the third root of x to the third is x. Right? So generally, we put these things together so that we can get rid of the denominator. So it'll divide evenly into the numerator. So try that one. Use the quotient property and see how it simplifies. Who got it? And you got 5x. Who got 5x? Anybody? Anybody didn't get 5x? You get it? So there's going to be two sets of problems that we do in the homework that are divide. And in the first set, it's always like this. You know, you can see, Josh, take it off. You can see that that's going to divide into that. I mean, you could just see it, right? 50 divided by 2, x is 6, x to the fourth. It's going to simplify. I think the next slide might be where it doesn't. Good. Okay, now the kind of problems where it doesn't simplify like that, we need to do what's called rationalizing the denominator, meaning we're going to turn irrational denominators into rational denominators. So an irrational denominator for us now means it's got some kind of a radical that can't be simplified in it, and we don't want it. And you did this before. right? You did this in geometry. If you remember when you did the special right triangles, right? One of them was called 45, 45, 90. Do you remember that? So in a 45, 45, 90 triangle, we had formulas for the lengths of the sides, right? It's isosceles, so these two are the same length, and we usually call it x, or sometimes they call it n, or whatever. It's a variable, and it's the same variable, right? And then the hypotenuse, it would be whatever that variable is times the square root of 2. That was the formula. I'm just reminding you of something you've done before, right? Then they'll give you, let's say, one side length that you know, and say find the other two side lengths. So if they give you, let's say they give us the hypotenuse of the triangle equals 5. Right? Then we have to figure out, well, how can I solve for x? Right? So I have to solve this equation, x times the square root of 2 equals 5. How do I isolate the x there? Divide both sides by square root of 2, right? So now we have x equals 5 divided by the square root of 2, right? That's what we mean by the irrational denominator, right? It's got an unsimplified square root in the denominator, and that's not acceptable. We always have to change so we have a rational denominator. And if you don't remember, the process you used to do that was to multiply the top and the bottom by the square root of 2. Right? Well, what is the square root of 2 divided by the square root of 2? It's 1. So really all we've done is multiply times 1. And what happens when you multiply a number by 1? You get the same thing back again, right? You don't change the value. So we're allowed to do that. It's not changing the value of anything. It's just going to make it look different. Right now, in the numerator, we have 5 times the square root of 2. Right? What do we have in the denominator? What is the square root of 2 times the square root of 2? 2. It's the square root of 4, which is 2. So that's what we mean by rationalizing denominator. Multiply by something to turn that denominator into a rational number. And it's not always, but for a square root, it's whatever is that denominator divided by itself. Do you remember doing that? Little? Yeah. Okay. Okay. So this part about monomial denominators, don't worry about monomial. Just next class we do binomial denominators. It's a slightly different procedure. Right? What would I multiply by? This one to rationalize the denominator. Right? It's got to be the square. It's going to be what divided by itself? The square root of 8x divided by the square root of 8x. Right? Whatever is this denominator times itself. In the numerator, use your product property. The square root of 5 times the square root of 8x is the square root of 40x. Okay. In the denominator, the square root of 8x times the square root of 8x is 8x. Right? That's like saying the square root of 8x squared. Right? The square root and the square cancel each other out. Okay, now we would have to simplify that. The square root of 40 can be simplified, right? 40 is not a perfect square, but what are the factors of 40 that include a perfect square? 4 times 10. So like if we make that a 4 times 10, then this is 2 times the square root of 10. So now this is 2 times the square root of 10x divided by 8x. Okay, now because there's a 2 outside the radical here, and that 8 is outside the radical, you can do some canceling there, right? 2 goes into 8 4 times. So that's the square root of 10x divided by 4x. Now, notice that you can't cancel these x's, right? Because one of those x's is inside of a radical, and the other one is not. Right? You can't cancel the 2 that factors into 10 with the 2 that factors into 4. right? Because one's in the radical, one isn't. We can only do this simplifying because both were outside the radical. Okay. Where? Here? 2 goes into 8 4 times. Right? Okay. Now, it's a little bit different. You got one homework problem like this too, because this is a cubed root, right? If I multiplied this one by the third root of 3x divided by the third root of 3x, right? In the numerator, I would have the third root of 15x. And in the denominator, I would have the third root of 3x in parentheses. That's wrong. Edit, undo, edit, undo. Of 3x in parentheses squared. But that's not enough for me to actually simplify that. What would I have really had to multiply this by in order to be able to get rid of the third root, which is in the denominator? I would have had to multiply it by the third root of 3x squared, right? Because then when I multiply these together, I get the third root of 3x to the third, which is 3x. That's what gets rid of it. It's not enough to just use this denominator exactly like it is. It's going to have to be the third root of 3x squared, so that when you multiply it together, 3x to the first times 3x squared is 3x to the third. Yes. And so if you do it there, then you have to do it there. And now you don't get 15x. Because this is going to be 9x squared times 5, which is 45x squared. So this is the third root of 45x squared divided by 3x. Here, well, we multiplied 3x in this one, which is to the first power, times 3x in this one, which was squared, is 3x to the third. And that's how many times you need it, right? You need it raised to the third so you could simplify a cubed root. Yeah. Here? Because remember, the whole goal is that we're going to be able to simplify a radical in the denominator so that there is no more radical. Since we're taking a third root, we need whatever is inside to be raised to the third power. Right? If I didn't have the 2 there, I would have 3x squared, which is not enough to simplify. So if I make this a squared, now when I multiply 3x times 3x squared, I get 3x to the third, and we know what happens with that. 3 divided by 3 is 1. So you get 3x to the first, no more radical. I mean, what would you do if it was, yes? Yeah, rationalizing denominator means get rid of the roots, the radicals in the denominator, the unresolved roots and the radicals in the denominator. Okay. So I think you've got one in the homework which is like that. There's one that's a square root that you can really just do it like you did with special right triangles. And then there's one that you have to consider the fact that it's a cubed root. You know, it could be a fourth root. Remember, if it was a fourth root, you need it to appear to the fourth power inside, so you can simplify it once. And that is it. So there's like 3 problems in most of these, like 3 simplify, 3 multiply, 3 divide, not to include rationalizing denominator, and 2 that you actually rationalize denominator.